but now that we are here, I'm hoping all of you are here to talk or listen to the edge compute and converged networks and the opportunities in 5G for Fronthaul and Backhaul. As the mobile and fixed networks are converging, it gives us a good opportunity to look at how we can harmonize the compute resources in terms of the location, the capabilities, so we could have more common infrastructure between the wireline and wireless networks. And from the wireless networks, you have the concept of multi-access edge compute that I think the cable networks can take advantage of. And if you look at the architecture of the cable networks today, you have the national data centers, the regional data centers, and the hub sites. And as we are moving to a more distributed architecture, these hub sites are collapsing. But we could use these hub sites for creating new data centers. And those data centers can be areas that we can combine the aspects of some of the core and some parts of the central units of the mobile networks, as well as as you have the virtual CMTS network. So there can be a lot of convergence that we can have on some of these locations. So we'll talk about the architecture of that, and then also what are some of the use cases that these things can enable, right? So as you collapse these things and create these new data centers, you not only can use these for network applications, but there'll be other use cases that are very latency and bandwidth sensitive. And so my esteemed colleagues are going to talk about that. The other part we'll talk about is on the 5G side. As we move from 4G to 5G, the data throughput required with 5G, as most of you know, is going to be about 100 times, or maybe even more, than what 5G handles today. And so if you use the traditional architecture that we use in 4G today, it's going to require extremely high bandwidth from the interface that you have between the radio units and the baseband. So what 3GPP has done is actually change that architecture. It's more of a split architecture where you change the baseband unit to what it's called the central unit as well as the distributed unit. And what that's going to help you do is it's going to reduce the requirements on the backhaul, not the backhaul, but the fronthaul as well as the midhaul. Because as you go into massive MIMO, you get into beamforming, those things, the amount of, if you use CPRI, the amount of bandwidth you need on these links on fiber, it's going to be extremely, extremely high. So again, we'll talk about how that split is going to help. So without further ado, let me quickly introduce my colleagues here. So I've got Rajiv Asathi, who is the CXCTO of Office. He's a distinguished engineer there at Cisco. And Joe Moserino, he's the solutions architect at Fujitsu at the optical networking. Right? And so let me quickly, Rajiv took the time to give me a little bit more detail about himself, so I'm going to say that. So Rajiv has, with global strategic and deep industry experience focused on digital transformation, he has incubated several cross-architectural and cross-technological solutions with specific outcomes and trusted advisory. He served on an advisory board for an IoT startup as well, and he has over 100 patents, 15 plus IETF RFCs, and a cable lab specification. So, Rajiv, I'll hand it over to you.
Thank you. Hi, good morning. There's a huge crowd I see. My God, like 300 people in the room. I can see all getting replicated in front of my eyes. Where is it going? I want to start off by asking ourselves a simple question. Where is the edge? And a fascinating thing is the answer varies depending on who you ask. For some of the over-the-top providers, where their definition of edge was somewhat in a centralized constructs, the data centers, is not very quickly changing. And here's the one from an entity that most of us are well familiar with, where they're really driving their infrastructure at the places that they can find as close to the users as possible. So the definition of edge is, of course, somewhere in the cloud for them. But the key there is that they're highlighting for their users of specific kinds, they want to get as close to them as possible. And interesting enough, from the SP, cable service provider point of view, that edge is one of the best. We'll get into that a little bit more, but keep that definition of edge. What could that be, and what possibilities could that bring to the cable construct? A big chunk of this is driven by the way applications have been changing. And these application changes are really fueling a lot of load and very interesting set of incentives for the networks in terms of high bandwidth, in terms of low latency, in terms of really better user experience. So on the top part of the slide, you would see the way these applications are getting somewhat deconstructed, decomposed, disaggregated, right? Whether they run on the leftmost side of bare metal or the rightmost side where these applications have been broken down into really minuscule pieces called function, and these functions can run at different places. Think about it for a second. MSO network, nationwide in most cases. Where could these functions, think of an application, the application you probably deal the most with could be an application that pertains to infrastructure such as CMTS, an application that could be as diverse as gaming. Think of that applications, or for that matter, IT applications, right? The very typical OSS applications, a billing application. Now, different set of requirements. If they were decomposed and disaggregated, they could be allowed to run in any of these constructs, and from the network point of view, they could be hosted in any of those locations where the application requirements could get satisfied. Clearly, a lot of magical orchestration have to happen to make this a reality. And the good news is a lot of that already exists today. The bottom right side is something that you might find interesting. As much as there's a hype and talk about containers and cloud native formats, the projection says a lot of containers would actually run inside the VM. Now, juries is still out there, but the trends are definitely indicating along that line. Now, if you start to think about these applications' evolution and the services as a result of them, and the experience that needs to be delivered to the endpoints, to the users. Now, users could be humans, right, the eyeballs, eardrums, or could be the ones without them, machines. The experience would be quite a very varying entity. But there are three important things that we have to focus on to derive the utmost benefit from MSO network point of view. One, on the latency reduction. And the latency reduction is becoming very, very critical. How many of you know that from the applications such as browser, once you start going above 10 Mbps data rate, it starts to make little difference if you go from 10 Mbps to 100 Mbps to 300 Mbps for the application specifically browser, the page load time doesn't really change much. I mean, maybe 5% gain, maybe 4% gain if you go from 10 Mbps to 50 Mbps. But what makes a huge difference to the page load time on an application such as browser is reducing the latency. And if the latency was reduced from, say, 2,000 milliseconds, or sorry, 3,500 milliseconds to, say, 2,000 milliseconds to 1,000 milliseconds, the experience could change. The page load time could change dramatically. It could go down by 50 to 60%. That's huge. And this is just one of many applications, browser, that we all use predominantly. Now, if you talk to an application such as gaming, the latency, the jitter, the packet drops, they all become really stringent. So anywhere we could host these applications depending on the requirements to reduce the latency, that could absolutely benefit the experience of the users. Now, applications I mentioned are more consumer-driven. They could be infrastructure application, right? So CCAP is an application. CDN caches, it's an application. So latency reduction becomes a key, and there is a, hopefully you can read that. So if you're hosting these applications out in the public cloud somewhere, the latency could be somewhere 100 to 200 milliseconds. As you start going closer and closer to the user, meaning as you start shifting the definition of edge from very centralized to somewhat distributed, the latency, of course, goes down. And that's why these public cloud providers, public gaming companies specifically, they're really gung-ho on moving the definition of edge. Now, in some cases, they can afford to do that. They're bringing their own equipment inside SP networks. In other cases, they're partnering, like Azure. They have been partnering with some of the service providers and advertising their edge locations as their own. The second one is data reduction, right? So think about some of the downstream bandwidth-hungry applications. Video is, of course, obvious one. That's in the downstream. How many of you think that the usage of upstream that's been somewhat muted all along is actually going to increase? Think about applications such as surveillance. My home, my upstream usage is not 10% of the downstream, which is typical in most eyeball networks. It's actually 60 to 80% of downstream. And in the white paper, you would actually see some stats around it, some actual usage. So if you have 3 cameras, 4 cameras, and you're storing things in the cloud, you're driving that upstream usage. So guess what? If all the traffic has to go through the ISP network into the public cloud, that's a lot of bandwidth growth that we'll have to deal with. You could take advantage of hosting them somewhere inside the network to really drive the bandwidth reduction, the data reduction. And the last, really offloading at the edge, again to drive different and better customer experience. So all of that has to be sort of come together, right, depending on the application requirements. And this notion of edge computing, or the cable edge computing, is really the construct to drive the hosting of these applications. Actually, you should say functions, because application could be decomposed in microservices, where each microservice is composed of multiple functions, and those functions could be running anywhere. So these functions could be hosted as closer to the user as possible. Now, how close? So I want to put that in the sort of end-to-end view. So it's a typical representation of a network. This looks pretty clean. I'm sure you would say that, well, the reality is not as clean as it looks. So where is the edge in this representation? Is it in the middle of the network? Is it somewhere in the data center, which are centralized, or it's the micro or mini data centers that are sitting in the pre-ag or in the hubs or in the access networks? Well, the answer is depending on the applications, they could be in any of those locations. And that's really key. The intent and the construct that we have to focus on, that there is no right answer for where that edge is. It's going to depend on the application requirements. So CEC, cable edge computing, that could be at the hub sites, well, which makes sense because for cable, the hub site is where the subscriber edge functions have been hosted all along. That's where most of the MSOs have their CMTSs, their edge comms sitting. Now with RPDs or the remote PHY, you're going even beyond, right, with the MAC PHY decoupling. Now, when we think about applications, again, from MSO's point of view, always have to think about, well, one, on the cable cloud, where the applications could be things like CCAP, things like gateways, in case of mobile-based services, and CDNs and IMS, and so forth. On the other side is the IT application that you have to host. You have been hosting all along. And these applications, of course, present diverse requirements. So then the question comes, all right, so if we have to think about these applications, and we have to think about, and we start to become severely exposed to their requirements, and we are presented with the daunting task of improving the network behavior for these applications, how far do we take? Should we put that right at the hub side? Should we keep them at the regional or the national data centers? Or even we take closer to the subscribers? And there are multiple benefits of distributing, right? As we have been talking, reduction in latency, reduction of backhaul, well, the network resources usage, you get a lot more awareness of locations where the given service or applications need to run. On the other side, we have to be wary of some of the negatives around the distributed construct, right? So it's highly perceived with that this brings operational complexity. And actually, I've been told by many smarter folks than I am that, well, actually for cable MSOs, not really that complex because MSOs have been managing those hub sites for decades. So if you're going to take the definition of these edge, the application-centric cloud, towards a hub site, it's not really as complex as you would think for other providers. And there's a truth to it. Right? The high infrastructure cost. Yes, so now if you have to transform these hub sites, as an example, into these application-centric clouds, that means a lot more x86 servers in place that may not have existed in the past, management of them, and so forth. Right? The third one is in fact, relevantly and a very pertinent one, which is the constraint that many of these hub sites may present in terms of space, power, cooling. So it's very important to be aware of the downsides. So many of the hub sites are constrained in one or more of those things. Many other hub sites may not have any constraints. So which of the hub sites get transformed at what point of time becomes very important. And of course, then the technology maturity, how can we secure them, and so forth. Now, it's not one or the other is the takeaway of this slide. Both of these models have validity in the cable SP environment, again, depending on the applications, okay? Depending on the use cases. So let's talk about them. And we really tend to think about these use cases in three big buckets: infrastructure, business to consumers, business to business. There are lots of research and studies out there that have been pointing to the fact that the revenue growth is not in B2C or infra, rather in B2B. That's where a lot of players in the industry are focusing on. So let's start with B2B. What could that be? Right? For many cable providers, having a mobile access and mobile-based services is becoming very important. For others, they have been offering the usage of their network in a wholesale kind of environment to other mobile providers. Right? So that's B2B. Now, that's going to continue, meaning MSOs giving the backhaul services to other providers. Could be other mobile providers, could be other cable providers, depending on the location. So locations become real assets now, especially the locations that are closer to the users. So the RAN is a good B2B example. IoT application hosting is another one. Gaming could be another B2B, right? Where essentially these transform hub sites could be now used to, well, host gaming servers. And especially the way some of the game streaming is going to work, it's going to actually require a lot of these sites to host the games. I want to focus on just one of these use cases and double click on it, which is the hosting of gateways. And in this picture, there are two different constructs, one on top, one at the bottom. So essentially pointing out the fact that these applications pertinent to service gateways, well, which are the ones that provide subscriber management, session management, policies, and so forth. So think of CMTS or CCAP. Right? That could be sitting in these sites along with the RAN applications, RAN workloads. So the decomposed RAN or decomposed node B would have DU, CU, RU. If they're virtualized, they could be hosted in these sites. So one on top suggests hosting them in the aggregation sites. One at the bottom suggests hosting them on the hub sites. Now, it's also important to think about, beyond these service gateways, what other applications could be hosted that would take advantage of these subscriber management functions. Right? So think of CDN. If you have the videos being delivered right from the hub sites, you save all that bandwidth from the backhaul point of view. Same, whether that's pertinent to cable subscriber, whether that's pertinent to mobile subscriber. So you could have your user plane function sitting at the hub site along with the cache, your own video, and you could be delivering that video to the user right from that hub site. And it's very important when we start to put this all together to drive an architectural that takes those challenges that we just looked at of these hub sites and many others and address them as much as possible. And one of the key incentives we want to take away, we want to drive, is really how we can optimize the stack, the architecture that yields significant savings than would it be possible otherwise. So there are 4 building blocks to make that work. One is really on the hardware side to build this edge infrastructure. The second is the software, the infrastructure software, not the applications that would run on this infrastructure, but the application software, but rather the software that will power these hardware. So think of Linux KVM, or think of OpenStack, or Kubernetes, and so forth. The third is the network fabric, which would allow us to connect all of these sites into rest of the network, whether it's on the internet side or on the consumer side or the user side. And the fourth, the most important, the automation, orchestration, and assurance block. So the first one, hardware. It's very important to choose the hardware, the x86 really, in a manner that allows to modularize. And in the white paper, we describe how we could construct these modular pods. And there is quite a bit of benefit, as we have seen one of the operators actually doing this, by minimizing number of SKUs that are possible. So you standardize and you modularize. So there could be a set of SKUs that you hone in on for the hub sites type A. This is the SKU, and that's it. And here's a SKU for another hub site. And where you consider, based on the use cases, where you need things like acceleration modules. So if there are use cases demand, like RAN, if you're hosting an application that is a DU, well, you need something that would be able to allow for processing of those TDM frames. Right? So those are very important. Once you have modularized it, it makes it a lot easier. Then the next is the software, the infrastructure software, which also has 4 key components. First, the cloud orchestration platform. Clearly, when you transform these sites into application-centric, you've got to be able to orchestrate these workloads and really be able to drive the requirements of these workloads. So what does a RAN workload require versus what does a CDN workload require versus what does a CMTS workload require? Bind them with some well-known attributes which would drive the notion of orchestrating these workloads at specific places. And it's very important to have this consistent, this common cloud orchestration platform. So today you could be dealing with OpenStack, could be dealing with Kubernetes, or something that comes along afterwards, right? Could be VMware. So it's very important to keep that as consistent as possible so you can cater to what these applications require. So if the applications are all in VM format or applications only in the cloud native format, you want to be able to accommodate for that coexistence. The second is really on the cloud controller nodes that get combined with compute nodes. Now, easier said than done. We tried that last year, and what we realized was that the deterministic NFV performance was gone. And we had to innovate quite a bit to bring that deterministic behavior back into the mix. And it's really, really critical if your use cases are going to be something like RAN that demand very deterministic behaviors. The CU, DU, they demand very specific behavior. And to make that happen, consideration that we had to make was to really pin the infrastructure management, right? So think of OpenStack or Kubernetes being nailed to specific cores so they don't start polluting cores that will be used to host those applications. Remember, Linux still has to run, and Linux needs its threads. And you can't afford to have them being shared. So it's very important to also nail those specific housekeeping threads on specific cores, thereby really freeing up all other CPU cores on that x86 nodes and all other x86 nodes in those sites to be available for services, those applications that pertain to specific services, right? And that's really, really key, whether cloud native or not. Third is to then look at decoupling storage, right? The image-based storage specifically, to move from these remote sites into where they really belong, where we can afford to have larger storage sites. Now, one of the interesting facts you might know, storage devices tend to fill a lot more than the typical compute devices. That means they need more maintenance. So if you were to put storage devices in the hub sites, and those happen to be unmanned hub sites, that's going to be a problem. The last one, be able to have all of the management be done remotely. Right? So the management node, that's usually a dedicated node that we can't afford to have it sitting in those hub sites if that's what we are going after. The third is really the network fabric. And it's important to base on any-to-any reachability. Now, when you start doing that, we run into multiple challenges. And so in the white paper, we actually have formulated a number of recommendations. Specifically, I will focus one, and I'll move on, is the hub site constraint that I mentioned earlier. And that can be addressed by optimizing the hardware and the infrastructure software that goes on, thereby making it much more palatable for hosting these applications of different requirements. So I want to summarize by saying that these hub sites in a distributed model are prime for transformation, prime for hosting these cloud-centric applications. And they're definitely very compelling use cases that would be palatable for MSOs. There are challenges, but thankfully we have a number of solutions that address them, and it's very important to focus on those architectural building blocks with specific innovations to optimize how we build that infrastructure to transform these hub sites. With that, thank you very much.
Thank you, Rajiv. We'll take the questions at the end of the session. So now that we have figured out, the whole virtualization, the cloud, cable edge cloud, Joe's going to talk about, what can we do with that, as we start to split the RAN architecture, as we look to virtualize these things. He'll talk about how that architecture of the split is going to work. So that Joe, who's the principal solutions architect, Packet Optical Networking and Fujitsu. Please.
Thank you. Well, thank you, everybody. My presentation is going to focus on front-haul, backhaul types of solutions, even a mid-haul type of solution. I have an agenda that I'm going to follow, and essentially this presentation and the white paper that we have posted is going to drill down a few levels further than what Rajiv was speaking of, but it's all along the same context in terms of virtualizing the network, cloud-based control of the network, how to address the network from where we are today in terms of the 4G RAN type of network, and then evolving to the 5G RAN. So I'm going to go through these various points. Let me start off with the basic building blocks of the RAN architecture. So many of you, if you are familiar with the 4G LTE architecture, you'll be familiar with this drawing or illustration that you see on the slide, which shows the remote radio head. This is on the farthest right of the illustration. This is at the cell site. This is actually the transceiver that's at the top of the tower that you see when you drive by these cell towers. Then at the base of the tower, around the chain link fence, there are cabinets of equipment. That houses the baseband unit, or the BBU. The connection between the two is a front-haul connection. It's essentially a cable between the top of the tower and the bottom of the tower going to the equipment rack at the baseband unit. The baseband unit supplies the processing for all of the calls and the data that goes through the cellular network. And then from the baseband unit, you then have a backhaul, which is using a carrier Ethernet technology to pass those signals on through to the evolved packet core configuration. So now let's look at the 5G network in contrast to that. So a little bit different. There's some similar areas, but then there's some new areas that we have. The 5G network is cloud controlled. So this is under SDN control. It's a cloud-based network. It is designed for virtualization. With the 4G LTE, you have CRAN, which was centralized RAN architecture. In the 5G RAN architecture, C takes up a new dimension. It's cloud RAN type of architecture, which offers virtualization to address multiple applications. So in these applications, and Manish had gone through this at the beginning of this speaking session, we have the BBU that is broken up into multiple pieces. The 3GPP essentially devised this so as to address the very high capacities of bandwidth that will be transported on that 5G network. If we were to use the same infrastructure that was used on the 4G LTE network to address the 5G capacities, the front haul capacities would be in the hundreds of gigabits per second for each channel. And typically there's about 12 channels at each cellular site that would have to be processed by the baseband unit. So in this case, the 3GPP split up the functionality, so there's processing that occurs in a distribution unit, the DU, and the central unit, the CU. From this processing, you have a reduction in the overall transport rate, which yields a much more attractive application set, whereas before, without doing this split, the transport optics alone would be price prohibitive in an access network, multiple 400 gigabit per second optical spans. There's also some functionality that occurs in the radio unit. This is the low-fi processing layer that occurs in the radio unit. This offers an eCPRI variable rate that is transported over the front haul being that section between the RU, that's at the radio unit at the top of the tower, to the distribution unit. The distribution unit could be at the tower, could be at some other location. It is a virtualized functional device, as well as the central unit. But these three units, the central unit, distribution unit, radio unit, make up the overall 5G RAN architecture where the central unit terminates that signal. Also, just to look at some of the latency budgets of these different spans, the front haul, mid haul, and back haul, I've listed them here. So they're very different from the 4G RAN in that you have the front haul optimized for 100 microseconds. That is 20 kilometers of fiber alone, consumes 100 microseconds of latency budget. And then the mid-haul, as low as 1 millisecond, that is Ethernet mid-haul structure, and the backhaul at what it was before at 10 milliseconds, similar to the 4G RAN model. So let's look at the different types of topology that one would implement for these types of networks. We have the distributed RAN. This is where all of the RAN components are at the cell site. So you have the radio units, the baseband units, and the backhaul is then achieved from that cell site to an evolved packet core. The centralized RAN is where you remove the electronics from the cell site, the baseband unit in 4G terms, and place it at a centralized location where you have multiple cell sites that are pooling on those baseband units to provide cell site aggregation, which is a performance increase for the overall RAN architecture. So by re-architecting the RAN, moving some of these building blocks around, you increase the performance by over 30%. You also simplify the engineering of the overall RAN by having this pooling structure. So centralized RAN is optimized, but it involves doing a front haul, which is a separate span. Previously was basically a cable from the top of the tower to the bottom of the tower, now turns into a whole new set of spans, transport spans, where you need transport equipment, dedicated dark fiber to transport that, but it does yield a major performance increase. And then we evolve to the virtualized RAN. This is where we still have the transceiver, the radio unit, the remote radio head at the top of the tower, but then all the rest of the electronics are virtualized. They're basically running on blade servers at different locations based on the location, as Rajit had pointed out in his presentation, is where the data center may be, where the latency may be at a minimal rate, at a more acceptable rate to address a more centralized type of architecture, and we're going to get into that as we move through the applications. But that virtualized RAN is where we're going, and this is where you have the cloud-based architecture. So in this drawing, it's quite complex, but this was an illustration of options that the Next Gen Mobile Networks Consortium developed last year, at the end of last year, for the different types of networks in RAN. You have on the leftmost side the centralized RAN architecture, where you have a central location, all your electronics and processing, and then you have the cell sites with the radio units, and then at the remote end, all the way to your right, you have the cell site RAN. This would be a distributed type of architecture where all the electronics are at the cell site. In between the two, you have different performance levels and latency aspects that can be achieved based on where you place the building blocks within 5G. I'm going to point out one in particular, this one in towards the center, where you have a network slice occurring. That network slice is occurring first at the cell site for a low latency type of application, such as autonomous vehicle operation or remote surgery operation, those where you need very, very low latency, otherwise referred to as ultra-reliable low latency connectivity. So you're terminating your session, your RAN session, right at the cell site via that central unit user plane. Again, a virtualized function operating on a server at the cell site. But then also for your centralized RAN, for your enhanced mobile broadband type of applications where you want to achieve that 30% or more performance enhancement by having a centralized RAN, you have another network slice from the distribution unit going to a centralized location where you have another central unit user plane function that's terminated at a centralized location. This is where multiple distribution units, which have multiple cell sites, all aggregated to it, to yield a cell site aggregation application, again, which yields a performance increase. So you see two types of use case applications where you have low latency and also a centralized network that can achieve high performance for enhanced mobile broadband type of applications on one infrastructure by using virtualization in the Cloud RAN application. To summarize all of these configurations, on the leftmost side you had the centralized RAN where you have the lower level split, but you have a high performance in your transport that can be realized through the coordination of gain from this centralization configuration. But then on the reverse side, on the rightmost side, you have the distributed RAN where you have a very low latency application. Performance is not as great, but you'll also have a cost savings because you don't have front haul transport that you have to worry about in terms of deployment. Let's look at the two types of radios, and then I'm going to get into the actual transport in front haul and different techniques that can be used on the front haul transport. So we have the two types of radios that are used in 5G or will be used in 5G are millimeter wave and sub-6 gigahertz radios. The millimeter wave is very, very high capacity. It's what AT&T and Verizon are deploying today for their fixed wireless access applications that are addressing residential and small to medium business types of high-speed internet service delivery applications. Very high capacity, but there's a major caveat: it has limited coverage. It doesn't go through buildings, walls, obstacles like trees very well. It basically doesn't go through them. So what you have to do in order to have coverage for a millimeter wave radio application is you have to deploy a lot of them, what we refer to as densification. You have to densify the application, work around obstacles like trees and buildings, and you have an outdoor application, and then you have an indoor application because it doesn't go through walls very well, and in fact reflects off of windows instead of going through them, which is what you have in the lower bandwidth range. And we're going to look at some applications that apply to that in the Fronthaul. Then you have sub-6 gigahertz, much lower capacity than millimeter wave, still very much higher than your 4G LTE that you have today. The coverage is similar to 4G LTE, which means they're going to be deployed at cell towers. Whereas millimeter wave is going to be on utility poles, on the sides of buildings. They're not going to be deployed necessarily on the traditional cell towers because you typically have blockage that will prevent the coverage from occurring. Sub-6 radios will be on the traditional cell towers, so very similar to the applications that were deployed with 4G LTE, we'll be using with the sub-6 radios. So now let's look at the different types of optical fronthaul options that are available with millimeter wave. You have dedicated dark fiber, which if you have a fiber-rich environment, this is the choice to use, but you need a great deal of this fiber. Just to do 4G at each cell site, you typically have 12 channels. To do 5G at a cell site, you'll have somewhere in the range of 6 to 9 channels starting, and that's many channels, many fibers. That's a pair of fibers for each channel that you would have to dedicate. And that's just one cell site. And then you have many, many cell sites, especially in urban areas. So where you're fiber-rich, dedicated dark fiber is a choice, but we don't always have that choice. So then there's multiplexing options using wave division multiplexing. And I'm going to get into time-sensitive networking in just a moment, but it doesn't really apply well to millimeter wave, and I'm going to tell you why. Basically because with millimeter wave, because it has to be densified and not at a traditional tower, you have issues where you need power to power an active type of solution, such as time-sensitive networking, type of aggregation, and that would be prohibitive to where you would deploy millimeter wave radios, such as a utility pole at a stoplight area at an intersection within a city. So using WDM optics, you have a full passive type of application where there's passive WDMs, wave division multiplexers at each end. Each of these wave division multiplexers are very small, about the size of one of these containers. They're all fully passive, so they don't require power. But then you have a limitation in that there's no remote visibility, so if there's any type of performance impairment, you won't know it until your customers start complaining that the performance is down or impaired, not working very well. So not the best, but it does provide an application for connectivity. Next comes a semi-passive type of WDM transport. And in semi-passive, you have active on one end, which would be a hub location, typically a head end or a hub type of location where you do have power and electronics and a place to put a rack type of equipment. And then at the cell site itself, you have a passive unit, doesn't require power, has smart optics installed into it. Those smart optics can provide a OEM channel to provide remote visibility back to the hub site. So you have this, essentially this low power, low cost, actually no power required, very low cost at the cell site. You still have remote OAN capability for remote visibility. And again, very small footprint, about the size of a coffee mug or large coffee mug or slightly bigger. So let's look at the sub-6 gigahertz applications. Again, this is where you would deploy these types of radios at a typical traditional tower. You could use a full active application of WDM or the new advanced IEEE 802.1cm time-sensitive networking application. So being that time-sensitive networking is new application, I've focused on that for the application, and I showed this typical point-to-point type of aggregation scheme that would be used both for 4G, 5G, as well as Ethernet traffic. The Ethernet traffic could be a spur that comes off of the cell site going to a business park or a residential development, offering fixed wireless access types of applications for high-speed internet, high-speed bandwidth connectivity. That would be aggregated over the same facility as the 4G and 5G approaches. The 4G and 5G would still be separate networks going to a central location terminated at baseband units, BBUs, or distribution units, respectively. Another application using additional processing would be using the ORAN Alliance techniques. The ORAN Alliance has a low-order physical layer 1 processing technique that was pulled out of 4G BBUs, put into 5G radio units that can be placed inside of a transport unit. So you can take a transport unit that's such as these TSN aggregation units, and transport your 4G and 5G traffic along with Ethernet traffic, but for that 4G traffic that's operating in CPRI, it can be converted to eCPRI for a more variable rate, reducing the capacity by up to 5 to 1, and as well as integrating the 4G and 5G network at the central site onto an open DU or a virtualized BBU. So now here's where you're collapsing your 4G and 5G network using this ORAN Alliance low-fi function to offer a converged network. So a major savings there. Another application for 4G RAN to 5G RAN is where you use the eCPRI 2.0 functionality. This is a transformation type of function where you would deploy the 5G radio units at that cell site, replace the BBU that was used previously for 4G with a virtual BBU or an open DU, and then convert the 4G remote radio head CPRI traffic to an eCPRI traffic using a remote appliance at that site using the eCPRI version 2.0 translation technique. So now I want to move into cloud control plane advantages in the overall virtualization of the network. We first look at traditional routers, and on a traditional router, you essentially have an integrated control and user plane where you have your chassis, there's a back plane on the chassis, you install control cards in that chassis, and then you have the blades which provide the line side or router functions for that traditional router. Initially, when these are deployed, they're deployed based on a time period of deployment for scaling, and that initial deployment's only using about 20 to 30% of capacity of those traditional routers. The rest of the capacity is basically unused but scaled over time, typically over the course of 3 to 5 years or more over time. But this is a very CapEx inefficient type of structure in that you still have to have the full footprint for that chassis, the full power maximum for that chassis, even though you're only using a small percentage of it, as well as the thermal reserve for that full chassis environment. And then as you scale the network, there's always the risk of over-engineering it because it's limited to the control cards and the chassis size and the number of blades that you could put in that chassis. So there's an alternate technique, and that's using the cloud control plane technique, which is similar to what's happening in the RAN using CUPS. CUPS is the control and user plane separation. This is the RAN version. On the transport side, we refer to this as disaggregation. We're disaggregating the control and user plane. By putting the control into the cloud-based network, we can scale the network much more easier, much more cost-effectively. One network unit can deploy hundreds of virtual routers from that one network unit, as shown here, so that multiple virtual router instances can be deployed from this one user plane infrastructure unit. You'll have a mesh of many of these in your network where you can rearrange the network to address all the different types of infrastructures based on the performance and use case that you need to address. Again, think back to that slide where I showed the next-gen mobile networks infrastructure of different topologies. How do you address all those different topologies with one infrastructure? Through virtualization, through cloud control plane scaling, which essentially yields a method to have decoupled control and user plane for a better utilization versus traditional routers. So let me just finalize with applying this to the actual application of network slicing or network slicing as a service. You start out with an infrastructure, a single infrastructure that has MPLS, segment routing, user plane, based capability, cloud control plane, and then as you fan out your network with different network slices, enhanced mobile broadband, ultra-reliable low-latency connectivity applications, massive machine type connectivity. These are the three typical application and use cases that are used in 5G. That's all can be provisioned from your basic infrastructure and rearranged with full resource guarantees and isolation between the control plane and user plane. So it makes for a very easy scaling method. Different customers are basically deployed through VPNs in the network, and essentially you have one common infrastructure with multiple virtual networks. So let me just finalize in saying this is where the networks are going. This is where the maximum flexibility and automation is going to be occurring in the networks, and it's an interesting aspect of the 5G infrastructure that we're going to be realizing. Thank you.
Thank you, Joe. We've got time for maybe one or two questions if there are any. Let's take them. Too early in the morning? Too clear?
Everybody got it.
Go ahead, please. If you want to move up to the microphone here.
Thank you guys for the presentation. It was helpful. One question about the transport. How's it going to be impacted when we are talking about multi-service edge? Today, when we have the MSOs, they have multiple services. I think you covered already on the RAN side of it, but when we are adding high capacity into the transport itself. How is it going to be evolved in order to prepare for the multi-access edge? It's not only on the hub sites, but also on the transport from the backhaul on the fronthaul side.
Joe, you want to take that?
Sure.
Yeah.
So great question. As I had pointed out in my presentation, virtualization is really where it's going to take place. Different capacities, maybe even just starting off, backing up a little bit, a fiber deep approach is what's required. So there's been some discussions about low latency DOCSIS. That can help in some areas, but not in all areas. Ideally, a fiber deep approach addresses them all. If the MSOs are looking for ways to attack, go after, compete with the telco vendors, they're going to have to go to a fiber deep approach, because if they continue to use, say, a DOCSIS-based method, they'll be limited in terms of what they can deploy. In a fiber deep approach, You basically have access to all types of technology, where we're going is a virtualized network. So you can reconfigure the network on the fly, on demand, at any time to address all the different use cases. The initial use cases of fixed wireless access, high-speed internet, enhanced mobile broadband, that's all going to happen initially as 5G rolls out and is happening now, in fact. But over time, we'll have those low latency applications that will be occurring. And how do you address the network? Do you build another network to address that? That would be cost prohibitive. If you have a virtualized network, you can easily adjust your network to address those new applications. So that's essentially how you would do it if you want to.
I think you summed it up really well. The 2 points I would just add, it would be really important to look at the trajectory that your organization would be on. Like what use cases that are being in focus today and what will be in focus in next 3 to 5 years. And then look at what the impact those use cases would bring into the network from end-to-end perspective. As Joe pointed out, what will be the impact on the access side? What will be the impact on the aggregation versus backbone appearing? And then devise the right side of usage in terms of the bandwidth impact accordingly. So in some use cases, DOCSIS might be very much useful. In other cases, as Joe pointed out, they may not be for last mile access. Now aggregation and upwards, 100 gigs and multiples of them clearly are gonna be the fiber-based approach that would make sense. But it's really important to look at the current and the forthcoming set of use cases that will drive the bandwidth and latency sensitivity in what part of the network and device accordingly.
Thank you, guys. I want to be respectful of time. Thank you again to the speakers, and thanks for taking the time to come at 9 a.m. Thank you, guys. Bye-bye.